Welcome to the technical information video on the test fuel and blowout stand senior project by Team 21 for Grand Valley State University, and the project was sponsored by Woodward, Inc. The team members of Team 21 consisted of Grant, who was the team captain, Chris, who was the assistant captain, Sam, who was the faculty point of contact, Tristan, the sponsor point of contact, Mike, the secretary, and Edgar, the assistant secretary. A brief overview of the video is shown here, going over the project details, the final build on all of its individual components, some additional features such as safety and storage, improvements made upon the machines, and special thanks. To give a little background on the sponsor of this project, Woodward Inc. is an aerospace manufacturer located in Zeeland, Michigan. Some of the products they produce are fuel injectors and afterburners, and these are for military and commercial aircraft. Woodward is a bigger international company, but this is what this plant does specifically. The main objective of this project was to combine 3 pre-existing machines at Woodward into one new compact machine. This machine needed to contain the functionalities of the 3 machines, and these 3 machines are able to clean the insides of fuel injectors. The cleaning that occurs is done through either compressed air or calibration fluid called test fuel. This test fuel would clean out any remaining chemicals from a chemical clean process external to the functionalities of this machine, and then the compressed air would dry out the inside of the nozzle. A few of the major specifications given by Woodward were to make the machine fit within a 6x3 foot footprint. It should be powered by a PLC and have an HMI screen for the operators, and a common adapter for the nozzles was desired and achieved in this project. The design stage of this project started back in January of 2024 and finished up in mid-May 2024, and it involved a few different stages. The first of these stages was to set the scope of the project, and once the scope was set, concepts were made, and prototypes followed this, including this CAD shown on screen right now. An estimated budget of $25,000 was made and approved by both the company and the faculty, and after this, a plan to move forward with the build was approved. Shown on screen now is the machine as it is at the time of the recording of this video. It is in the final week of the build, and all the components are present. There's a lot going on in this machine, so I'll go into detail on each of the components. The first section I'll go over in detail is the HMI and PLC of the machine. Shown here is the interior of the PLC panel. It ranges from power supply to fuses to jumpers and all the above. This is what powers the motor on the machine and allows for compressed air and test fuel to run through the parts. Seen on top here is a stack light to show the status of the machine. The HMI screen that the operator will see is shown here. They can input the number of nozzles being used, up to 8 nozzles, and they can start either the air or the fuel runs, and these settings are set in the engineering sub-screen where pressures and time intervals can be set. A demonstration of operator input is shown here. Where the air gets quieter here is where the pressure is decreased to 40 psi. Shown here in the mounting plate are our pneumatic components, and I will go into detail about each of them. On the left side here, an air hose can be plugged into our shutoff valve, which will allow air to either run through or not run through, which has been really helpful for testing out the components. Following this is a filter and an initial air regulator to get the 300 psi shop air down to something a little more reasonable for a second regulator, which can lower the pressure to either 150 or 40 psi based on input from the PLC. The second air regulator then goes straight to our air manifold, which has 8 solenoids control the output. Output can range from 1 to 8 hoses based on the input from the PLC, and this air goes directly to the part. The underbody view of the manifold is viewed here with temporary hose placements in for testing purposes. A demonstration of the air running through the valves is shown here with lower pressures due to Grand Valley not having a 300 psi shop air connection. The hoses coming out of the manifold go straight to our other mounting plate, where 16 hoses are shown, where 8 are for the air and the other 8 are for the test fuel. These hoses are connected to the adapters of the parts, which go directly into the parts obviously, and then they are set on top of this mounting area, where air is blown as waste into the right tank shown. Next, I will discuss how the fuel components work. The fuel is run through the system and is powered using this Baldor 5 horsepower motor and is coupled to the pump shown here. A 20-gallon reservoir is used to house the test fuel, and the outlet of this goes directly to the pump, which is kept horizontal to keep a constant feed to the pump. The outlet of the pump goes directly to a relief valve where the pressure is dialed down. For the fuel that the relief valve doesn't let through, it returns directly to the reservoir through a 1/2-inch tapped hole we mounted at the top. The fuel that is let through the relief valve goes straight to a 10-micron filter in case of any contaminants within the fuel after being recycled. Following this, the fuel goes into our 8-piece manifold, where needle valves and DK lock fittings are utilized to control the output to the 8 hoses. The DK lock fittings make it possible that only a few different hoses can be run at once in case you're only running something like 3 parts at a time, as it is currently set up to be shown here. The hoses then go directly to the back plate. The nozzles are mounted in a similar fashion as the air setup, just in the left tank. And to recycle the test fuel, an outlet at the bottom of the tank goes directly back to the reservoir, along with the bleed valve from the pump. Now we'll talk a little bit about the caster wheels. 4 of the red caster wheels shown here are used on the machine, and they were purchased from Caster Depot. Each wheel has the potential to hold up to 300 pounds, combining for 1,200 pounds total, which is nowhere near the weight of our machine for safety. Speaking of safety, let's talk about a couple of things we added. Like many machines, ours contains an e-stop and is placed at the front of our PLC panel for easy access. We also 3D printed the e-stop ring around it for higher visibility. In addition to this, a disconnect switch from Allen Bradley is used because of the high voltage we're using. Let's now talk about the storage of the machine. A stainless steel shelf has been placed on the lower right-hand side of the table, and this is available to store FOD caps or some of the adapters for the various parts used. I'm now going to talk about some of the obstacles we faced along the process of this build. The first of these is lead times, where a lot of the parts we ordered did not come in time or were back ordered, but the big hindrance is that we started ordering parts later than we originally intended, sending us back a couple weeks. The next big obstacle we ran into was the electrical side of this project. All of us are mechanical engineers on this project. Where we do have a little bit of electrical knowledge, it was a challenge to learn a lot of these components. A big thank you goes out to Sam on the team, who took the blunt of a lot of the electrical work, as he had a little experience in PLC building, and without his work and some help from Woodward, this machine would not be what it is today. Time was also a concern, as mentioned earlier, as we started a little bit later on the build than we originally intended, as well as all of us having additional classes on top of the senior project build. We definitely learned some lessons along the way as well, ordering some wrong parts that didn't work with the machine how we thought they originally would, so we had to wait a little longer to get the correct parts, and this plays into the time and lead times issues we experienced. On a different note, I would like to talk about some of the improvements that our machine makes upon the current process that exists at Woodward today. The current process as it is today is shown here in yellow, purple, and red, where a singular part has to move among 4 separate machines. The new process is shown here in green and red, with red being the external operation of M56 chemical clean, and it is easily seen with combining the 3 pre-existing machines that a lot of time is saved. To be more specific, an estimated 50% time savings was calculated, and this can be attributed to us running more parts at once, because currently only one part can have fuel flush through it at a time, and on our machine up to 8 parts can be run at once. Operator movement around a cell does add more time than someone would think. Moving around 3 to 4 different machines, cutting that down to 2 saved a lot of time as well. And finally, probably the most important of the time-saving contributors is that common adapters are being used on all of the machines. Currently, different adapters are used on the 2 fuel flush stands, the air flush stand, and the M56 chemical cleaner, but in our project we figured out how to utilize the chemical cleaner adapters to be used on this new machine, so once the parts enter this cell, the adapter can be put on first and remain on through the use of all machines. We wanted to give out a special thanks to Paul Arms, Adam Klingensmith, and Rex Beach of Woodward for the continuous support throughout the build of this project, in addition to the GVSU labs for the help on the 3D printing and the use of their machine shop tools. I hope that you enjoyed learning about our machine. Once again, a special thank you to Grand Valley State University and Woodward, and thank you for watching.